even better. So what I'm going to describe for you as electrically small antennas is to overcome what are traditionally trade-offs for small antennas. So the approach I'll emphasize is the one that we've developed over the last 25 years, which is near-field resonant parasitic designs. So our first opportunity to demonstrate electrically small antennas was to do efficiency. And what made it possible is that we can use this paradigm of the near-field resonant parasitics to do impedance matching without any external circuit elements. The driven elements simply excite the resonators, and the currents induced on them is actually what produces the radiated fields, and that's what actually helps with the efficiency. And as you will see, input impedance is matched directly to circuits. So that's useful. Bandwidth, I'll touch on bandwidth. It turns out that electrically small antennas are notoriously very narrow bandwidth. So we'll show you some examples of how we overcome that with some recent thoughts on metasurfaces and also with active elements. So, and then directivity. There'll be a little bit more emphasis on directivity because it's one of my very current interests with antennas. And so I'll show you Huygens dipole antennas and actually some super directive electrically small antennas. So these are useful for a variety of space-limited applications, and here's some of them, right? So mobile platform. So if you think about your automobiles now, you definitely are connected with many, many different forms of communication, whether it's just simply GPS, or if you have a more modern car, then you have radars in the cars that have to give you warning about collisions. I will give you the example that one of my former PhD students, Aijan Arentak, who you'll probably hear some comments about him later in the presentation. Aijan is currently the lead of all antenna engineering at Tesla. And so the Tesla Model 3 has almost 30 different antennas embedded into the structure. And so that's definitely a mobile platform with a lot of connectivity possibilities, right? With monitoring health, here's one thing is sports. So when I was in Australia, this is my Fulbright, it turns out that people like to bet on sports. And the idea is they started having different sports people wear, in essence, monitors. So you could monitor real time. So sensors monitoring heartbeats, sort of feeling out how strong they are versus weak after performing a half quarter of footy. So it really helped with betting, right? So, and here for people of my age, right? So you have to worry about wireless health monitoring. And so different kinds of on-body kinds of antennas. Definitely don't want to have a reflector antenna on your body to help with monitoring. So small antennas provide a role. And I'll show you some examples of where drones come into play with having small antennas. Right? So what is a small antenna? So by definition, electrically small, you find your entire antenna and you enclose it in the smallest sphere whose radius is A, and then Ka being 2 pi over lambda A. So in essence, the radius of the sphere relative to wavelength. If Ka is less than or equal to 1, you can say it's electrically small. So that's basically a radius of about lambda over 7. But I will emphasize, because I'll bring up issues of directivity. Directivity is the maximum that one can get for gain or realized gain. Gain is efficiency times directivity. Realized gain is how well you're matched times efficiency times directivity. So if you can get 100% efficiency and everything is perfectly matched, then the maximum gain you can actually get, realized gain, is in fact the directivity. So I'll be emphasizing directivity more than, say, gain, right? Okay, so here's where we start with electrically small. So I'd say everyone that has taken at least an undergraduate course in electromagnetics, you've been faced with thinking about the small electric dipole. So this is the complex power associated with a small electric dipole, and you can see the kind of movie that you would find, for example, on wiki. In fact, this comes from Wiki, all right? So Wikipedia has this nice little picture. You can see that it's radiating, but this is what the power actually looks like. And you all know there's a radiation resistance, which is the real part of the complex power. And then it turns out for a small electric dipole, it's a highly capacitive element. So you can see if Ka, if it's very electrically small, then the capacitance is very, very large, right? And that's what makes it very difficult to match to basically a 50 ohm load. It becomes difficult. And moreover, to get it to radiate effectively, you really have to match to free space because you don't want to have any, quote, impedance mismatch to free space, right? So the traditional approach is something like this. So you take your small dipole antenna, and it's highly capacitive. And what you normally do is you introduce some kind of inductor into the circuit that's driving the electric dipole. So that gives you a resonator, right? And the idea is to have, where it's resonant, you'll have your reactance to be 0, right? And so then you hope it's radiating well, right? And this is a typical antenna when I was young and cars were, so this is in the like 60s and 70s, you'd have a whip antenna, and this piggy tail, right, is actually an inductor. And so that would help you have a shorter antenna that was reasonably efficient to radiate, right? So you still have to worry about accepted power and worry about overall efficiency with these small antennas, right? So it turns out lecturing in my junior, actually it was the antenna class is actually at Arizona was senior year master's kind of students. And so it was a joint undergrad graduate kind of class. This was right after metamaterials. So I'll describe how I got interested in metamaterials. And the idea is a double negative metamaterial is one where the epsilon is less than 0 and mu is less than 0. And so I was amongst the first to publish about metamaterials in our community, right? So the issue is this is the power again, and notice this looks like highly capacitive. So what happens though if you have some kind of double negative material? So if you write K in terms of omega times square root of epsilon times square root of mu, and both epsilon and mu are negative, then what you find is in fact that K is less than 0. And that means this term will actually become a positive reactance, will become inductive, right? And so this is an issue with double negative media, that the wave vector, in essence, the phase propagates opposite the direction that the Poynting's vector propagates in terms of the power flow, right? So, but that led us to do the following. Alison Kipple was a PhD student with me, and we ended up looking at a small ideal dipole enclosed in a double negative shell. So you end up with a double positive region and a double negative region, and it turns out you can make a very, very tiny resonator. In fact, this example, it was smaller than lambda over 50. And it turns out to be highly resonant. And this is a comparison of that antenna radiating in free space versus radiating in the presence of the double negative shell. And you can see it's a highly resonant dipole, right? And so this is interesting. But you can also do the same thing in scattering. So you can actually make an electrically small scatterer that in essence has unity cross-section. So this whole thing started out with being able to have electrically small resonators. And this goes back now over 20 years, right? So, okay, so the whole near-field resonant paradigm boils down to having a small radiator and a small resonator in the presence of it. You get reactive matching, so it looks like a resistor, and then that resistive matching to free space is what definitely gives you good power output from your device, and then you end up with a strong response with this combination. It's resonant, and it's a very low loss resonator, right? So turns out that I call it metamaterial inspired when we introduce that term, because I'm going to show you examples where we only have one unit cell of something that would be like a metamaterial for our antenna. It's not a bulk medium, although I'm going to talk about that shortly here. So how did I get interested in metamaterials? So I will tell you, I was invited and participant in the original DARPA workshop in November '99, where the term metamaterials got invented and metamaterials actually got launched, right? So I got invited because in the late '90s, got interested in how we could make, in essence, realize a perfect match layer. So I was doing a lot of computational electromagnetics at the time. And there was a revolution in absorbing boundary conditions in '93 called the perfect match layer. Béranger introduced it, but it turns out that some of us wanted to know if we could make a perfect absorber in real life. His approach actually was a mathematical trick. And we were interested, could we make a material that would be a perfect absorber? So the way we started looking at it was we would take like electric molecules. So we'd have electrically small dipole, but then we'd put a load on it. And what that gives you is actually a way to control the dispersive scattering that occurs from this small electric object. Then we take a small magnetic object, do the same kind of loading, and we were looking at putting together small electric elements, small magnetic elements to make artificial molecules and atoms right, at the time. So that's what got me to the original DARPA workshop, right? So I was participant in the original workshop, and then I was part of one of the first DARPA-sponsored programs that Boeing led. And the issue was, at the time, this is the first double negative metamaterial. This was a split ring resonator with cut wire on the back. This was Schultz and Smith and our good English friend whose name is escaping me, Pendry. So in terms of being able to look at this material, we were tasked by DARPA to make a unit cell and hence a metamaterial that would be lambda over 60 or smaller, right? So the idea, 10 times smaller material. So the way we did it was we made use of the ideas that we had introduced. This is our electrically small epsilon negative unit cell. It was basically a lambda over 100 in size. It was a small inductor with a meander antenna. And then we made a small magnetic unit cell, which was a split ring, which we call a capacitively loaded loop. And in fact, there was a capacitor here to enhance the capacitance. And this was lambda over 100. And we designed it so we could put the two together as one unit cell, and we actually had a lambda over 75 unit cell. We made a bulk metamaterial and measured it, and we met all the criterion, and we were able to do 2 more years of work under the program, and that's in fact when a lot of our original metamaterial inspired and based antennas happened. But the problem was these unit cells were in fact too large to make electrically small metamaterial based antennas, because to make a bulk metamaterial, you like to have 3 to 5 unit cells in the direction of where your wave would be propagating. Well, if 5 unit cells here makes it still pretty big, right? 5 into 75. You can see that it's still reasonably large, and to make it all come together, it wasn't possible. Right? So this is how we ended up realizing these metamaterial inspired antennas. We took the small dipole and we then put a resonator in the presence. So this is called an Egyptian axe dipole. It's a near field resonant parasitic. There's an inductor here for tuning purposes. Egyptian axe is actually, it came from my watching the movie The Mummy, and then sort of the creatures use these Egyptian axes during the battles, right? And so it turns out to be nicely matched to the driven element. You can make it happen. And you get tailoring the near field to get reactance matching, and you tailor the currents to get resistive matching to the source and to free space. And this is the kind of the first original design of a Egyptian axe dipole antenna. And you can see that it turned out to be very matched, frequency agile, and tunable, right? Because of you can change the inductor value. And it turned out to be very efficient, right? Over 90% efficiency for an object that was electrically small, right? And you can see where the main currents are. Underneath is the driven dipole, but on the top is the Egyptian axe dipole, and that's what's actually radiating strongly, right? So when I was a distinguished chair and professor in Australia, I worked with Defense Science and Technology Organization. They actually created the position for Fulbright, and I was in the Advanced Materials Division in Melbourne. And they were very interested in integrating antennas into carbon reinforced materials. So if you want to take a current car that's very light, it's usually made out of carbon reinforced material, or an airplane, you know, sort of all the most recent aircraft are usually some kind of carbon reinforced bodies, right? Could you embed the airplane, or could you embed the antenna directly into them? And so we ended up sewing one of my antennas into, in essence, it would be the carbon reinforced material before it's put into a conclave under high temperature and high pressure. So this is still flexible. We actually sewed the antenna in, and then we tested it. But after we did that, the team in Melbourne, basically Kelvin Nicholson and Thomas Baum, Kelvin actually walked me in and out every day into the secure facility that was the DSTO. And it turned out they came up with a copper veil that you could actually laser cut. So instead of having to sew, they actually were able to cut shapes and then put it into, integrate it into the prepreg, which is this carbon reinforced material before you make it hard. And then we tested them all, and it turned out that all of them, in fact, radiated very efficiently, and they were all very well matched to the source. And so just most recently, I was at UCAP, and I was part of the sort of finalists for Best Paper Award. And the poster right next to me, actually, Kelvin was a co-author for it. And the young man that was presenting, actually, they got the award. And what they did was they took one of Stefano Macci's kind of antennas, which would be a monopole driving a metasurface, and they made the metasurface integrated completely into the surface of a carbon reinforced curved object, a conformal kind of antenna on a body. Right? So it's a very interesting concept. This is an example of where it was actually done for a application. This turns out to be a unmanned aerial vehicle, so UAV, for ice penetrating radar. And it turned out this bottom body, you can see the shape, it's actually an Egyptian X dipole. I communicated with the lead author. She explained to me that in fact it was very attractive and it worked very nicely for their design. So this actually works, right? Okay, we tried all the different combinations you could have. So it doesn't have to be electric with some kind of electric system. Here's an electric drive with a magnetic element. This is a capacitily loaded loop. You can see electric with electric. You can see here a magnetic. So this is a wire antenna that's a magnetic dipole. It's a semi-loop, so there's a ground plane here. And then you have, again, the capacitily loaded loop. And this we call the protractor antenna. You can see the capacitily loaded loop, and you can see the monopole driving it, right? So you have all these different elements and all the couplings. We studied them and found how you could make them. In particular, here's a very interesting one. So this is very electrically small. At 100 megahertz, you can see the sort of size scale here. It's a very low profile. It's lambda over 25. And in fact, this was measured at NIST Boulder. This was made by Boeing. And in fact, it was measured with over 98% efficiency. This was a more complicated version. So there's 4 resonators here. This was for CP realization of GPS L1 and L2. So L1 is the larger structure, and L2 is the smaller structure because it longer wavelength or shorter wavelength. And in terms of you have them integrated in such a manner that you get a particular phase variation of 90 degrees between the two sets of resonators, and you can see the driven elements on the back side here, and it works quite nicely. Again, this was highly efficient. So here's an example of making use of this type of antenna in practical situation. And so there was an interest. So Scott Tayo was a professor at optical sciences at the U of A. He the kind of history has always been with applied electromagnetics, but he had a team that he worked with before coming to Arizona. He was at the University of New Mexico, and he worked with a company called ARL in Albuquerque, and they were interested in high power microwave systems. And so they would develop high power microwave sources, and they wanted a nice antenna to put it into a very small compact object. So we ended up making this design and testing it, and then I made a spherical version to actually put into an object such as this, which you can imagine what it might be used for, right? So if you're doing high power microwaves, you want to be able to put very high power energy into your antenna and to have it radiate efficiently. So these small antennas actually worked up to about 100 kilovolts in terms of the sources. And so, these have a number of different applications, right? This is a more exotic electrically small antennas. I got interested in thinking about plasmas because I did a lot of work on plasmas when I was at Lawrence Livermore Laboratory after my PhD. And one of the things we know when we teach our junior level class is that the ionosphere, right? We know that AM radio at night will actually go large distances, whereas it won't during the daytime. And the reason for that is that the plasma density in the ionosphere changes between daylight and nighttime. And what happens is, in fact, that your permittivity at night becomes negative in the ionosphere, and so the waves reflect off of it. And so you end up with a highly reflective kind of situation. But the point is that it becomes negative. And so the idea here was, again, our small source. We put it into a glass, spherical kind of a shell, and we had a plasma inside, and we said, theoretically and modeling wise, could we make this radiate efficiently in an electrically small system? And we did, right? And it turned out the plasma density would be just like what you have in a fluorescent bulb. If you hadn't realized, fluorescent bulbs are actually plasma waves, and that's, you excite the plasma wave in the bulb from one end, goes to the other end, and your light comes out, right? So it turned out that in 2019, I was at UCAP, and a team from France actually made this happen. And so you end up with putting a plasma inside this hemispherical shell, and in fact, it radiated very nicely and efficiently, and it was electrically small. So if you're a theoretician and you put out an idea, you wait long enough, somebody might try it, and in this case, it was successful. Now, in terms of directivity, why we're interested in directivity? Well, it turns out that we have a variety of new networks coming into play. We have the space network, along with a terrestrial network, but also a mid-layer network. So these would be things like drone systems or high-altitude platforms, HAPS. And the idea would be is to use them for relays, or actually to use them as base stations themselves in the sort of mid-layer. In fact, if you were to look at IEEE spectrum, there was a very nice article almost now about 6 or 7 weeks ago where there's a US company that makes dirigibles. They are flying a dirigible over to Japan, working with a Japanese wireless company to use the dirigible as a base station. So you could position the dirigible at a reasonable altitude and to use it as a base station. So the idea of highly directed systems can mitigate the issues of low power sources and overcome large propagation losses, particularly if you're talking millimeter waves. And yet it also provides a low probability of intercept, so you can have more information transmitted securely. So high directivity has applications. All right, so to have a single source antenna with high directivity, this is what you normally have to do. Remember from, again, your junior class, that you'd have 4 pi aperture area over lambda squared as the directivity. So if you make your aperture bigger for a given wavelength size, you can get higher and higher directivity. So this is deep space network. This would be an old-fashioned TV reflector antenna, right? So we tried to do it in a lot of different ways. One of the first things to use metamaterials back in the 2000s was to make artificial magnetic conductors. The reason being, if you want to make a low-profile antenna, if you take an electric dipole and here's your ground plane, you all know that what happens is that your image is in the other direction. So if you take the dipole and put it closer and closer to the ground plane, the image and it get closer and closer together, and you can get cancellation, right? So if you take an artificial magnetic conductor, on the other hand, artificial magnetic conductor, it turns out the image is in the same direction, so you end up with doubling, right? And it turns out that the Mushroom Surface by Seven Piper in '99, and then Tatsuo Ito's EBG kind of structure, they all had ground planes. And the issue here was we actually made an artificial magnetic conductor as a bulk metamaterial without any ground plane. We actually designed these capacity loaded loops, and then we, sort of in essence tested it with a dipole. And this, you can see our block of artificial magnetic conductor, right? And so it worked quite nicely. On the other hand, if you had noticed on the chart with the epsilon and mu's, there was a red dot in the center. It turns out that if you want to make a zero index material, you can. You can make epsilon and mu zero at the same frequency point. And so we actually looked into trying to make a highly directed system. And it turns out why? Because if you take a patch antenna, you end up with something like 3.2 dB, but then you put in essence, this was a bulk metamaterial at the time, over it, and if it has zero index, that means the phase across the aperture is uniform. And it turns out that any kind of aperture antenna, if you have an area and it's a uniform amplitude, uniform phase across the aperture, that's the best directivity that you can get. So in this case, this particular design upped the directivity from 3.2 to 17.2, and this was at 60 gigahertz. So Steve Franson was a PhD with me. He was working at Motorola at the time when they had a millimeter wave team up in Phoenix. And it turned out that they tested this, and so this is back in 2008, 2009, getting 2 gigabits per second. Ethernet was quite a success at the time, right? And it was possible to do that. I was interested in electromagnetic band gap structures from the optics work that I was doing in the 90s, and we tried to make electrically small systems using EBGs, and it turned out that we couldn't really make it small enough, right? We'd get on the order of Ka being 1 with very high epsilon materials. At the time, it was hard to get low loss, high EPS material. And now you can actually get epsilon 100 with loss tangents smaller than what you get with Rogers toroid. So it would be possible to go back and maybe think about these things. But actually, it was pretty decent concept, right? On the other hand, I wanted to do more unidirectional. And so unidirectional would be power in the maximum direction versus power in the back direction. That's your front to back ratio. And I'd like to get a front to back ratio greater than 10. Right? So here's how we are thinking about doing that. So you can take combinations of electric and magnetic dipoles, and this is multipole engineering, so this is your first introduction to it, and to make a cardioid pattern with it. And so what do I mean? So it's not so different of any things that you've been taught so far or experienced so far. We've done a lot of things where we have mixtures of dipoles. So here's most common is a turnstile antenna, a cross dipole where you have electric along X, electric along Y, and you put a 90-degree phase difference between them. That's how you get a CP antenna, the turnstile. Right? So it works quite nicely. Right? This is what I'm going to emphasize, the Huygens dipole antenna. And so I'm going to take an electric dipole, orthogonal magnetic dipole, and if you balance them properly, you can actually get this cardioid pattern. So it turns out for ideal elements, you have a front to back ratio that's in fact infinite. right? So you end up with doubling it in this direction, as you will see on the next slide. And then this is kind of what the pattern looks like in 3D. You could also take the electric dipole and magnetic dipole and make them parallel, right? And so what you get is an omnidirectional CP antenna. So with Wei Lin, who was a postdoc with me at UTS in Sydney, we actually made this at 28 gigahertz. He's currently an assistant professor at Polytechnic University in Hong Kong. But we actually made this at 28 gigahertz and it worked very nicely. This is another version, which is electric and magnetic orthogonal, but the magnetic is 90 degrees out of phase with the electric, and you can make what's called a Janus or quasi-isotropic antenna. So you end up patterns like this. So Alex Wong at CityU Hong Kong has actually done some of these designs at microwave frequencies. Zayet's from the UK has done a lot with photonics related things originally. Okay, so this is the Huygens dipole antenna. The idea is you take electric current, orthogonal magnetic current, right-hand rule gives you the direction of where the cardioid maximum is going to be because it looks like this. So you have a electric current, and you can see what's important here is notice the way the electric fields are, right? This one's even, and this one's odd. This is the magnetic dipole. You can see the top and bottom are opposite, top and bottom are the same. But these top and bottoms, of course, cancel, and that's what gives you the cardioid pattern. And you can see you get it in both the electric field behavior and the magnetic field behavior. So that's pretty cool. You get a nice unidirectional system. So can you do it in practice? And so the answer is yes. What that gives you is basically a kind of a directivity maximum. Instead of 1.76, you get twice. So instead of 1.5, it's 3 or 4.77 dB. So this is the original sort of Huygens dipole antenna that we did. So this goes all the way back to 2010. So the idea here is that you have two pieces of toroid with a driven dipole sandwiched between those pieces of toroid. On one toroid face, you end up with the Egyptian axe. On the back toroid face, you end up with two protractor elements, right? So you can see the protractor element, right? So capacitily loaded loops, and it radiates in the end fire. So it goes away from the source in this direction. And you can see it was highly efficient, quite nice realized gain. And oh, so all these simulations were done with HFSS. So in terms of this is, that's been the primary thing that used for these small antennas because it gives you, as a frequency domain simulation tool, it's one of the more accurate ones, right? Okay, so I wanted to make something that was broadside radiating. So broadside radiating, in fact, is done the similar way. So I have a coax-driven dipole. Here's your Egyptian axe, and you have the capacitily loaded loops. And you put the two together, and you have a broadside radiating system. In fact, it looks like this. It's unidirectional. Front-to-back ratio is very nice. You can see the radiation efficiency is great. In fact, the peak directivity is actually a little bit better than this, and the realized gain is quite good. And so you can see it's electrically small. Ka was 0.45, and the radiation efficiency was close to 90%. So this was kind of the first design of Huygens dipole antenna was made immediately afterwards, right? Since then, we've done a lot of things. We've made multifunctional and reconfigurable Huygens dipole antennas by using multiple near-field resonant parasitics. And here's 3 examples. Ming-Chun Tong was a visiting PhD student with me in Tucson. He has a very nice team at Chongqing University in China, and we've collaborated actually since he was a PhD with me, right? And the idea is that here's a pattern reconfigurable system. Each one of these Huygens dipoles covers a 120-degree sector in the azimuthal plane, and using switches, you can actually switch the azimuthal plane covering it entirely. Here's a polarization reconfigurable. So this is actually, how should I say, orthogonal Huygens dipole antennas with switches that you see here with the driven elements that you can turn on the different, in essence, excitations of the resonators. And you can see you can get both LP, both LCHP, and RCHP. So you can get 4 reconfigurable polarization states in an electrically small package. And electrically thin one. This was interesting because with switches, you can see the Huygens dipole here embedded in a piece of toroid, so very thin. And this one radiates in this direction. This one radiates in this direction. There's going to be a change in a few slides, but they radiate in opposite directions, or you can turn them on simultaneously, so you can cover both directions simultaneously. And so it's a very nice little interesting thin design. And of course, we always build and test, right? So they're all tested out to agree with the simulations, right? Now you can do more. You can actually introduce circuits into the near field resonant parasitic elements. And also, of course, with the driven. So one of the things I was really interested in and have been is in wireless power transfer. So what is wireless power transfer? You have a AC power source on the antenna emitting waves, and you have a rectenna receiving them. So a rectenna is a combination of antenna and a rectifier. And the idea is you receive AC and you convert it into DC for the application. And you like to get it as high a possible conversion efficiency. So here's a CP antenna that was designed. This is again with Wei Lin, right, who I mentioned earlier. And so these are two orthogonal Huygens dipole antennas integrated together. And the interesting thing is this is a rectifier circuit that was embedded into this. You can see it down here, right? And the idea is that we could match the antenna directly to this rectifier. You can see the rectifier is not 50 ohms. And you can see the antenna was not matched to 50 ohms, but it was matched actually to the rectifier, because the rectifier is what you want. We're powering this by a wave coming in. It's not matched to a 50 ohm source. So this system antenna was matched directly to the rectifier. And in the LP version, we got close to 90% conversion efficiency. And in the CP case, we got over 80%. And you can see little pieces here in terms of the entire structure, but these little dipoles, by changing the lengths of them, you can actually introduce phase, like a 90 degrees phase shift to give you the CP. So, okay, for those of you who are students, of course, one of the things in the annual meeting for APS is that there's always a student design contest. So this was coming out of COVID, and the meeting was the first one out of COVID. It was in Denver. And I thought it would be interesting to have a student design contest because it talked about small antennas. So I talked to Ming Chun. He put together a team Bloom of Youth from Chongqing. So these are undergraduate students and master's students. And we actually took one of our antennas. It was one of the KA52 sized ones. So this is that CP antenna. And we integrated it with a thermal device, one that could measure temperature. And that turned out to be, you put in essence, a sensor tag on a person to measure temperature wirelessly. And why that was interesting is I thought it'd be nice. In COVID, one of the problems was to measure temperatures, you'd scan your forehead with a thermometer, right? And an infrared device. Well, that puts you in immediate contact with a person who might have COVID, right? And so the idea is, could you measure temperature remotely? And so we came up with something that at the time was more than a factor 10 better than what was being sold on the market. And it was basically wirelessly monitoring temperatures on a body. Okay, so bandwidth, I'm running a little over, so we'll see how it happens here. So bandwidth, turns out in 48, the true limit basically says if you look at the quality factor of an antenna, it looks like 1 over Ka plus 1 over Ka cubed. So if Ka is small, your quality factor, all right, gets huge, and as a consequence, your fractional bandwidth gets tiny. In fact, it goes like Ka cubed. So if you have electrically small antenna, generally the bandwidth is in fact small. Right? So how do you get over that? Well, you can combine your basic antenna with some kind of structure, again, electrically small, that would cause multiple resonances to occur in the same sort of frequency band. And when that happens, you have overlapping resonances and hence very nice instantaneous bandwidth. Another way is you can overcome the fundamental properties that gave the true limit, which were linear time invariant assumptions. And you could do it by putting energy into the system that causes you to be able to get non-Foster behavior. So this is an example of one of our CP antennas where we introduced a grid structure over it. Again, this is with Ming Chun's team. The idea is that what happened with the grid array is actually it pulled down one of the resonances associated with the original elements plus a resonance that was on the grid structure. So this is the bare CP antenna, and then putting the grid structure over it, you can see a higher order resonance got pulled down into the same region as the original resonances, and as a consequence, you got bandwidth that went from 3.7 up to 30% impedance-wise, and then the axial ratio bandwidth was greater than 20%. And so this worked very nicely. Actively, we've been involved with active matching networks for a while. Non-Foster, I'll remind you of the Foster theorem says that changes in permittivity and permeability with frequency have to be increasing with increasing frequency. Non-Foster means that they actually can decrease, right? So what people wanted to do is take a non-Foster kind of elements there, and this original paper by Sussman, Fort, and Rudish were trying to match resistance and reactance actively to the antenna to actually get instantaneous bandwidth, right? So I thought it would be interesting to actually put these active elements introduce them into the near field resonant parasitic elements, and then have internal matching possibility. And so our first design, this was a design, so this goes back to also to Peng Jin back in 2010. We took a copper cap, we had these non-Foster inductors as the legs, a monopole coax antenna, and this turned out to be land over 130 in radius, right? It turned out to be Ka very small, and we demonstrated over a 10% bandwidth. Right? With Ning Zhu, again, a PhD student with me, we actually took the Egyptian axe and we put, you can see this turns out to be a non-Foster circuit, right? So the antenna size is Ka 0.49, and embedded it into the near field resonant parasitic. And we are actually able to go from, fractional bandwidth of 1.4 up to 8.5. And it turned out to be almost a factor of 6 times the directivity over Q bound, right? So it worked very nicely. And there have been many examples of using non-Foster elements since then, right? This is a more interesting one in some senses. This is our most recent kind of version. So this just came out. So I worked with Silvio Harbar in Zagreb University. Silvio has done a lot with trying to make broadband metamaterials. And so the idea is to do these kind of non-Foster or transistor-based active elements. But he came up with an interesting concept, which was if you take two antennas, like antennas, but make them orthogonal to each other, you could use one as a reactive matching to the other one. One would be the radiator, and the other is, in essence, a reactive load to give you, in essence, a resonance, right? And you can actually tune it. So we demonstrate that you could tune it by putting in a tank circuit, or you could make it into amplifying kind of a system as a reflection amplifier mode, right? So you can see it. This is pretty big. We're measuring at 10 megahertz, so that was a decent size antenna, but it's electrically small, and it went up to 100 megahertz, so that was a 10-to-1 bandwidth. And over the top 10% of that bandwidth, it was actually unidirectional. The original design, I had hoped it would be unidirectional over all of this, but it turns out that it was some of the things you needed to do for the magnetic dipole or electric dipole at the lower frequencies wasn't working as well as had been hoped, right? But demonstrated a 10-to-1 bandwidth. And you can see typical university measurement, right? So you put it up on one roof and you measure over on the other roof, right? So it's, but it worked quite nicely. All right, can you do better? So I'd like to do better. And the way we do that is with multipoles. Why multipoles? The issue is that Harrington in the 50s through analysis of vector spherical wave expansions, demonstrated that the maximum directivity you can get from an antenna that has a multipole of order m would be m squared plus 2m. So if you can go from a dipole to a quadrupole or octupole and so on, you can get more directivity in your antenna. Can you do it? So how do you make a multipole? Well, we all know if you take two point charges, which are monopoles, right? So you can see each charge, this one comes in, this one goes out. But if you put them very close to each other, hopefully you did this in your junior ENM class, is that in fact you get an electric dipole, right? So the monopole fields cancel and you're left with a dipole. So how do you make a quadrupole? You take two dipoles of opposite sign, and it turns out you can see the symmetry here. This one's even, but this one's odd, like what you have with a magnetic dipole. And you can see this versus this, right? What about an octupole? Well, you take two quadrupoles, which is four dipoles, and you orient them appropriately, and you get an octupole behavior, and so on, right? Okay, so this is what it looks like in HFSS, right? So you end up with HFS simulation for the dipole. Looks like a good electric dipole. But then you take two of them or four of them, and you can actually get the next two orders of spherical wave expansion. So this is the second order associated with Legendre polynomial, and with m is 2 and this one is m is 1. So these are both second order spherical wave expansion terms. All right, so what happens to make it real, right? So here's a real system. So Rocio Rodriguez-Cano visited me at UTS in November 2019, and we designed this antenna, which is a driven dipole with these two plates that are, in essence, you end up with currents in opposite directions. So these are quadrupole plates. And this dipole quadrupole antenna was designed to work at 28 gigahertz. It was supposed to be measured. She went back to Aalborg University in Denmark, and then COVID happened. So, sort of February, January 2020, she could no longer get into the high frequency fabrication and measurement laboratory, but she could get access to the lower frequency lab. And so we actually redesigned everything to work at 1.6 gigahertz, and it worked very nicely. Okay, so I'm going to finalize with some more fancy stuff, right? So it turns out Harrington predicted that the maximum multipole you get would be on the order of Ka for the size of the antenna. So there's this normal directivity that people use to make comparisons against, Ka squared plus 2Ka. And if your directivity is greater than that for an end-fire radiating system, then you could call it superdirective. For a broadside radiating, we still go back to our original 4 pi A over lambda squared, which becomes Ka squared for a circular aperture. But if your maximum directivity is greater than this, then in fact, it's superdirective. All right, so how would you make a interesting Huygens quadrupole antenna? So this is our original Egyptian axe, the original capacity loaded loop monopole, I should say magnetic dipole, electric dipole, and their combination. So this goes back to the original thing I showed you from 2015, right? So I also demonstrated in the paper that you could make it go in the other direction. So what happens is by changing sort of the relative distance between the Egyptian axe and the driven dipole, as well as the capacity loaded loops, you could actually make a phase change occur for the current on the Egyptian axe. So with them in the wrong direction, I showed you it had to be, J cross K gives it. So if it changed the J, it goes down. And so here, in fact, is the result. Can you use it? Well, this is how we did it. So here's two Huygens dipoles, right? One driven element. And you can see this distances between the Egyptian axe and the dipole are different. And it turns out that this radiated this direction. If I had the same distance, this would radiate that direction, like I showed you with the ultra thin case. But here we changed it, and as a consequence, they both radiate this direction. And it turned out to be this kind of a pattern where the directivity was over 6.6 or 7.6, and as a consequence, it's super directive. But also you can see the realized gain was very, because it's very efficient, it was also super gain. So this is a super gain Huygens quadrupole antenna. This was yet another version of taking into account a magnetic dipole. So you can see a coax here comes up and it's connected, and this gives you a loop, right? So that's magnetic dipole. But then the way that it's situated, you get currents flowing this direction on the top bow tie, currents flowing this direction on the bottom bow tie. And what happens is that because they're slightly different in size, you have a little bit leftover electric dipole, you have the magnetic dipole, and then you have the quadrupole. And you put that together, 800 megahertz, it's electrically small, it's low profile, and in fact, this is the maximum directivity for this broadside radiating system, and this is what was measured, right? So it was very super directive. And the realized gain, super gain, and radiation efficiency was close to 95%. Tiny bandwidth, but it worked, right? Okay, so to do more, right? So a couple more slides and we're finished. So it turns out Ming-Chun wanted to try something where it wasn't parasitic, something where all the elements were driven simultaneously. So there's one source, but this cross feed allowed us to actually distribute the currents on each of the strips of this 3-element electric system. So these are all electric dipole strips. We got the currents on them that had the proper phase and proper amplitude that was predicted by, in essence, an optimization algorithm. And so this was measured to have over 8 dB. It was not electrically small, but then we took a generalization of the previous antenna that I showed you. We took the 2 bow ties and then put an Egyptian axe in between. And this combination actually got more than a dB better than that original quadrupole dipole electric plus the magnetic dipole. This is 3 electric elements. So this was, in essence, dipoles and quadrupoles together, and we got a very high directivity, and it was again super directive, right? And overall efficiency is over 80%, so it's still good. And yes, it was small bandwidth. Okay, last examples, right? So you could do more. So U antennas were very interesting for many years because people thought they could make isotropic antennas using U elements. It turns out if you take 2 U elements, you could make them resonators, right? They're resonant objects. But if you put the phase on them so that the currents go in the right direction, as shown here, you can see the top here, or bottom here, they're opposite. So you can see I'm trying to make a quadrupole kind of a design like this. And here's the antenna. So it turned out that we split the 2 in essence. So this was the Egyptian axe, it was split. These rings give you impedance matching to the source, right, which would have to be a tapered balun. And then it's electrically small element and low profile, high over efficiency, and the directivity was over 7, right? And so it even beat the multipole bound of Harrington by a little bit. And that meant there's actually a little something quadrupolish, octopolish going on here. So we thought, all right, what happens? Can we do better, right? So we did. So an E element, so you can see the E elements is split into 2 U elements, and you can see if you had them with opposite currents appropriately, you can make something, in fact, that would be resonant, and you put 2 of them together and you can get the currents oriented in the right direction again. That, in essence, gives you a dipole, quadrupole, and octopole behavior. And here's the examples that were measured, right? So this was high conductivity 3D printed aluminum alloy. This was a CNC machine brass material. This one was electrically small, and we got 8.6 dB, right? So this actually is definitely super directive and super gain. I wanted to see what happens if you went a little bit bigger in size. So this is Ka, a little bit larger than 1. And in fact, we got up to 10, right? So the 3 Egyptian axes, they were slightly off shifted with these impedance matching elements. And here, it turns out all the Egyptian axe elements are in the same vertical plane. And so, yeah, we did quite nicely. And here's a summary of all of them, right? So these traditional bounds, so this turns out the Harrington normal directivity. This turns out to be the 4 pi a over lambda squared. This turns out to be a heuristic bound developed by Kidell and Best. It turns out that both of these go to minus infinity when Ka gets tiny, right? Which isn't physical. Even a tiny electric dipole, you know, it's 1.77. So with a tiny electric dipole, tiny magnetic dipole, I've already showed you it's got to be 4.77. So they actually kludged a bound, which was Ka squared plus 3, and that's the Kidell bound here, right? So you can see all the antennas that I showed you surpass those bounds, and they're demonstrated, in fact, that they're all super directive and have super gain. So I've shared with you a number of different electrically small antennas, examples of prototyped electric and magnetic dipole systems, prototype electrically small Huygens systems. We achieved large bandwidths with both active and passive elements, and we've actually made super directive unidirectional mixed multipole antennas taking advantage of, in essence, multipole engineering. Okay. So I will conclude by saying if you want to read more about all the different papers that I've talked about, you can find them on my Google Scholar page, right? So you can trace them all down. This is the original metamaterials book that we did. And I have to put a plug in for our daughter. Daughter's a graphics designer, and she, in fact, did the cover for our book back in 2006. So this is one of the first metamaterials books. This is my original finite difference time domain modeling of a double negative material. Double negative here, you can see negative refraction occurring, right? And so this is kind of cool. And this is, in fact, 2 books that I was involved writing during the COVID. And so you can see this was one, Jay Goh was the head of the center that I was in at the University of Technology, Sydney. Definitely you can tell this was Australia emphasized. And here, in fact, was the most recent book. And I bring this up from the standpoint that chapter 10 I wrote is all about electrically small antennas. So more or less what I've showed you today. Chapter 12 is interesting. I was a co-author with Inigo Libero. So if you want really, really tiny electrically small antennas, this is all about quantum antennas and quantum arrays, and so you can make use of the classical concepts to make some interesting quantum devices. And actually, chapter 11 is interesting because it's also quantum. It's Rydberg atom sensors by Chris Holloway and his team at Boulder NIST. And I'll put a plug in. If you want to hear more about multipole engineering, I'm giving one of these new distributed distinguished lecture webinars. One just happened, so I'll be on board in June 11th, so you can sign up for it. Okay, that's it for this morning. Sorry, I went about 10 minutes more than I wanted to. I get involved talking, and it was nice sharing with you all these different things. So thank you. I'm open for questions. I'm here. I'm not running away. Thank you, Jack.
Yes, thank you so much, Prof. Yes, at this point, I'd love to take any questions that someone might have. And really, thank you so much for the lovely presentations, breaking down the various antennas concepts, and yeah, from materials, and then now for us who've already just gotten this slight introduction to antennas, then getting this deep dive into the electrically small antennas and the various prototypes that have been done and the various applications in the various areas, and just seeing the practicality of antennas in the field. Yeah, I think that has been really great. Yeah, so thank you so much. Thank you so much, Prof. So anyone with questions, I'll open the floor to questions. Yes, Daniel.
Rich, can you hear me well?
Yes.
Excellent. Great presentation. Covered a lot of ground very quickly. Question for you is the directivity does not imply a high front to back ratio. Am I understanding that correctly?
In essence, yes. So,
If I want,
I was just going to say,
if I want,
something like a patch antenna, right? A patch antenna, you have front to back ratio that's on the order of 6 to 7, but it's all based with ground plane. So
is it possible to get high directivity and high front to back ratio?
well, that's what I showed you. Yes. In fact, that is the whole point, and without a ground plane. So there's no ground plane in any of those designs.
And we're doing this in electrically small devices.
Correct.
Okay, thank you.
Thanks. Bradley?
Yes, you shared a link to some of the books that you've written. Could you paste that link in the chat?
What do you mean by a link? The books aren't available as link to my personal account or something like that. No, those they're copyrighted by IEEE Wiley, so that's something it's not possible.
Oh, I see.
Yes, Rick, I think is referring to the Google Scholar where you said if someone.
Oh, the Google Scholar page. Sure.
Yeah, the Google Scholar page. Yes.
Let's see if I can. I can bring it up here. So, all right. So how do I share that?
Just give me a minute. I think I can figure out how we can do that, and then
yeah. No, in
just...
terms of I don't know how to open up like a bubble and put it in. That would go to everybody. Pop up in call messages.
And then Tony.
Okay, thank you for the presentation, Prof. Now I've actually posted my questions on the chat, if you can read. But let me go through it quickly. So I was saying I'm currently an MSc student at JQuat. But as you were doing your presentation, I did find most of the equations and the concepts you have presented are quite actually new to me. It was quite embarrassing for me, considering we did most of this class in undergraduate still on masters. So my two concerns were basically, so the second question was, how do these equations translate, or the process of translation of these equations to real life products? And my main question, which I'm coming at, I'm currently doing my project, and I'm doing something on smart antennas. So what I'm getting from this presentation is that the field of antennas is quite large. So my project has narrowed down on smart antennas, and my approach to this, the project is minimization of side lobes in smart antennas. My question is, if you are familiar with smart antennas, how do engineers in real life minimize side lobes in smart antennas with the intent of improving, achieving or improving or maximizing gain and achieving better directivity?
Okay, so it turns out there are, usually when you're talking side lobes, then you're actually talking some kind of an array, right? So the way that you can change the side lobe levels is by tapering the amplitudes of the elements in the array. So you can actually, instead of being uniform sort of phase and uniform amplitude to give you maximum directivity, you give up some of the maximum directivity to get lower side lobes. And the way that you do that, you put a taper on the amplitude, as well as you can change some of the phase distribution on the array elements as well. And that allows you to get lower side lobes. So there are a couple kind of distributions that people use, like a binomial distribution for the tapering, or Chebyshev distribution. There are several well-known sort of ways to have the amplitudes on the array so that you can lower the side lobe levels. In fact, you can design the array so that you can have very, very low side lobes on the order of 30 dB down kind of side lobes, right? So those would be in, I think it's chapter, for example, if you have a copy of Blanis's antenna book, be like chapter maybe 12, so that basically the arrays, he describes the Chebyshev as well as the binomial distributions. So those are very typical ones. So the idea is you have to give up usually something to get the lower side lobes. So you, instead of having your maximum directivity and very low side lobes, that requires a lot, maybe other things. Instead of having a uniform distribution of the elements, you might have something like a random distribution of the elements where it's been optimized through some optimization algorithm to give you low side lobes and as much directivity as you can get with the number of elements that you're using. Hope that helps.
Yes, it kind of helps. I was actually thinking of using optimization algorithms like evolutionary algorithms to do the optimization process. So I just wanted some guide to know if I'm on the right track or.
Well, you are. I mean, there are so many different optimization algorithms now. In fact, I gave a similar presentation Wednesday, and similar question got asked, right? So topological optimization is one that people use, right? So that's where you say, nowadays, of course, people are interested in meta surfaces. So if you give yourself a surface and then you say, I'm going to have elements that are copper that are going to put on the surface, and then you let this topological optimization program where you say, I'd like to have high directivity, low side lobes, and it will actually design the shape of each of those inclusions on the meta surface to give you that. So yeah, there are a number of ways to actually think about the optimization to give you what you're trying. So, but there exists a number of examples in the literature. So that's yeah, that's the best I can help you with, right? So it's a very general question.
Okay, yes, and lastly, I hope it is not embarrassing. It's embarrassing for me to ask. So I'm asking, this was the very first question. How deep do you go on this course in wherever you are? Because for us, I think we did something to do with Maxwell equation, and then those TM, TE. I think that is where we ended the course. So
Okay.
as you were doing the presentations, most of the equations appeared actually very new to me. I was actually asking myself, what did I study in school? So I'm asking at your level, either in BSc or master's level, how deep do you study this? Do you teach your students on this?
So in terms of teaching the students, so the undergrad first electromagnetics course would be, things on the order of free S equation, things like the 4 pi a over lambda squared, just, sort of more general kind of things. But as soon as you got to a senior level course, like the antenna course, I would actually go through, all the electric dipole, magnetic dipole with all the equations, not just far field, but actually what happens in the near field, the mid-range, far field. Then in the antenna class, of course, then I would talk about arrays. So you have all the formulas that are associated with arrays, with aperture, or basically aperture kind of antennas. So something like a ground plane with a circular aperture in it, which is also in Blanis's textbook. So I used Blanis's text for the antenna class, and we basically went through about the first 14 chapters in terms of explaining the equations, and then the students actually got to use HFSS, and they designed patch antennas for their final project. So they had to make a linear pole and then a circular pole patch antenna, and we would take them into the clean room. They would fabricate it, and then we would measure it to see how successful they were. So in the class, they got exposed to theory and then numerical, and then experiment. So that's the way I handled. And this would have been a class that would have been the senior levels and some master's level students in it. Now, in terms of further, the stuff where you start to do scattering, like to do vector spherical wave expansions, to do plane wave scattering from spheres, or plane wave scatterings from cylinders, or plane wave scattering from wedges, or even maybe a dipole scattering from something like a wedge or sphere. That would be the advanced theory class. So that was really more along the lines of what PhD students were looking at in my advanced theory class.
Okay.
Yes, thank you so much. Thanks so much. I think we'll take the last question from Khan.
Hello, Khan.
Okay. Hello, Professor. My question is related to quattro polar antennas.
Okay.
I've seen you made a dive from dipole to quattro polar antennas. I had an idea of doing a drone, which is I use a patch, but I had a problem with it because it was only radiating in one direction. So my question is, the quadrupole antenna, the one you designed, was it radiating as a omnidirectional, or it was still a directional antenna?
It was actually primarily unidirectional.
Oh, okay.
But that was by design. That was, so the way that it was structured, it was hard to see, but there was two parallel elements, like I showed in terms of quadrupole, right? But the slight shift of them, they were not directly on top of each other, they were slightly shifted. The shift gave you impedance matching, but the dipole was driven, it excited those elements. And the way that it was arranged in such a manner that, in fact, it was primarily radiating, broadside to the aperture of the quadrupole, but by design. So if you wanted to go in both directions, it would probably be possible if, instead of having the dipole here and then the quadrupoles, above it, you might actually be able to move it so you're exciting primarily the quadrupole, and then it will be in both directions. In fact, the one slide where I showed the example of, let's see if I can go back to that. Right here. So if you look at this, you can see the pattern. So this particular design right here, so having two driven elements does what you want. It goes, bidirectional. It's totally bidirectional. This one, because of the split, it's may not be as interesting for what you'd want, because it's not bidirectional per se, but it's radiating the same in the upper and lower hemisphere. But this one's definitely bidirectional, and it's just two elements driven oppositely. Right? So that would give you what you said you would like to have.
Okay, thank you.
Yep.
Okay, thank you. Prof, will allow me to take just one more question from Jess.
Hello, Jess.
Yeah.
Okay, Jess.
Hello.
Hello. I like your flower.
It was a great presentation, first of all. I am quite new to, I felt like I was listening to a foreign language. So my question is, what would you suggest is a good way to get into antennas? Like, which books or what should I get into as somebody who's interested in antennas? I do a space, so we kind of.
Okay, so well,
not really that much.
Okay, so in terms of books, right? So I always used Blanis's antenna theory book, right? So I think he has, it's edition 5 now. So I've taught out of editions 2, 3, and 4. So from the standpoint, it was, for me, it was very popular. In terms of sort of more on the theory side, he actually has an applied electromagnetics theory book that I liked. A lot of people used Harrington's time harmonic fields book. Even though I used a lot of Harrington's things in terms of what I talked about research-wise, I didn't like the book because of his definition of, in essence, the vector potential, the magnetic vector potential. It's not the same as one would learn, for example, in physics, or it's not the same as you would have generally nowadays in electromagnetics. So I never actually used time harmonic fields as a textbook. But Blanis's book is both the theory book and the antenna books are very well written. There's a lot of examples in them, and you could find most of what you need to get started in different aspects of antennas from his book, right? So, but you know, I have to tell you that when you talk about getting books to study and to learn from, everybody learns differently, and so there's a book that you can get online. Let's see if I can. Orfandus, he's a professor in New Jersey that the book's accessible online, and it's not too bad. It's ORFANIDIS, Electromagnetic Waves and Antennas, and it was online, available in 2024, and if you like, I'll, because it was asked, I'll share my Google Scholar page, and I'll share the link to this book to Jack after we're finished. How's that?
Yeah, I think that will be great. Thank you.
You're welcome.
Yes. Thank you so much. Thank you so much. We can all give a round of applause to Professor Richard Ziolkowski. Yeah, it has been a great presentation, and I thank you so much, Prof, for sparing your time just to take us through this. And we do hope that one time we'll be able to host you in Kenya when you now come to now speak and interact with us physically. Yeah, we can plan for that. And yes, it's been great having you, and hope to hear more from you and even into the future as we continue looking at more about antennas and how to just innovate in the areas of antennas and even its applications, and just invent newer things to be applied in various areas of the industry and to just help the communities outside there. So thank you so much. I think if you're in a position, for those of us who are in a position to have our videos on, you can just have your video on and then say hi as you exit. I don't know if mine is on. Yes, so
I'll just simply say thank you all for being here. You know, so it's a pleasure with so many of you here on a Friday night. I definitely appreciate it. And Jack, thank you very much for organizing all of this. I hope someday that I will actually be able to visit Nairobi and your university. It would be fun.
Sure. We can plan for the same, because I'd also really love to host you in Kenya and to teach you a few Swahili in Kenya. Yeah, so
I appreciate that.
Feel most welcome. Yes,
Again,
looking forward to more sessions with you. Yes.
Okay, thank you all.
Okay, you have a good day, and the rest of us who are in East African time, have a good night. Those who are in Europe, I think you're just getting into your evening, so you too have a lovely evening. Thank you all, and see you in the next one.
Right.
Goodbye.
Again, thank you. Adios.
Adios, muchachos.